Okay, so the formula that we remember is really dw by ds in the direction of u is gradient w dot product with u. And maybe I should also say in words, this is the component of the gradient in the direction of u. And maybe that makes more sense. So for example, the directional derivative in the direction of I hat is the component along the x-axis. That's the same as, indeed, the partial derivative in the x direction. Things make sense. dw ds in the direction of I hat is, sorry, what am I doing? Gradient w dot I hat, which is w sub x. Or maybe I should write partial w or partial x. Okay. Now, so that's basically what we need to know to compute these guys. So now let's go back to the gradient and see what this tells us about the gradient. I see you guys are having fun. Okay. Okay, let's do a little bit of geometry here. That should calm you down. So we said dw ds in the direction of u is gradient w dot u. That's the same as the length of gradient w times the length of u, well, that happens to be 1 because we're taking a unit vector, times the cosine of the angle between the gradient and the given unit vector u. So have this angle theta. Okay, that's another way of saying we're taking the component of the gradient in the direction of u. But now, what does that tell us? Well, let's try to figure out in which directions w changes the fastest, in which direction it increases the most, or decreases the most, or doesn't actually change. So this is, when is this going to be the largest? If I set a point, then the gradient vector at that point is given to me. But the question is, in which direction does it change the most quickly? Well, what I can change is the direction, and this will be the largest when the cosine is 1. So this is largest when cosine of the angle is 1. That means the angle is 0. That means u is actually in the direction of the gradient. Okay, so that's a new way to think about the direction of the gradient. The gradient is the direction in which the function increases the most quickly at that point. So the direction of gradient w is the direction of fastest increase of w at the given point. And what is the magnitude of w? Well, it's actually the directional derivative in that direction. Okay, so if I go in that direction, which gives me the fastest increase, then the corresponding slope will be the length of the gradient. And what's the direction of fastest decrease? it's going in the opposite direction, right? I mean, if you're on a mountain and you know that you're facing the mountain, that's the direction of fastest increase. The direction of fastest decrease is behind you, straight down. Okay, so the minimal value of dWds is achieved when cosine of theta is -1. That means theta equals 180 degrees. That means u is in the direction of minus the gradient. It points opposite to the gradient. And finally, when do we have dWds equals 0? So in which direction does the function not change? Well, we have two answers to that. One is to just use that formula. So that's when cosine theta equals 0. That means theta equals 90 degrees. That means that u is perpendicular to the gradient. The other way to think about it, a direction in which the value doesn't change, is a direction that's tangent to the level surface. If we are not changing, it means we are moving along the level. And that's the same thing. As being tangent to the level. So let me just show that on the picture here. So if I actually show you the gradient, you can't really see it here. I need to move a bit. Okay, so the gradient here is pointing straight up at the point that I've chosen. Now, if I choose a slice that's perpendicular, in a direction that's perpendicular to the gradient, so that's actually tangent to the level curve, then you see that my slice is flat. I don't actually have any slope. The directional derivative in a direction that's perpendicular to the gradient is basically 0. Now, if I rotate, then the slope slowly increases, and it becomes the largest when I'm going in the direction of the gradient. So here I have actually a pretty big slope. And now if I keep rotating, then the slope will decrease again. Then it becomes 0 when I'm perpendicular, and then it becomes negative. It's the most negative when I'm pointing away from the gradient, and then becomes 0 again when I'm back perpendicular. Okay? So, for example, if I give you a contour plot, and I ask you to draw the direction of the gradient vector, well, at this point, for example, you would look at the picture. The gradient vector would be going perpendicular to the level, and it would be going towards higher values of the function. And I don't know if you can see the labels, but the thing in the middle is a minimum. So it would actually be pointing in this kind of direction. Okay? So that's it for today.